So the next talk is about synthesizing vectorized code via verified lifting by Jeremy.
Okay. Okay. Is my mic on? People hear me? Cool. So my name is Jeremy Ferguson. I am from UC Berkeley, and today I will be presenting synthesizing vectorized code via verified lifting. So we'll go ahead and start off with some motivation. Why do we care about this problem? So to illustrate this, we're going to look at this first code sample here. You can see it's written in standard Python, and it's pretty easy to tell what's going on. You've just got your two for loops here. You're iterating over an array, and then in the middle there you've got this if statement. And what it's doing is computing the rolling sum of consecutive C's and G's in a sequence of characters. And so it's very expressive, it's very clear, but it's also very slow. And so we can compare this to our next code sample here, which is written in NumPy. And so what it's doing here, it's the same code, it's semantically equivalent, but it is done using vectorized array functions. And so in comparison, it's a lot harder to read and write to figure out what's going on. For example, the concatenate, you've got a false concatenate at the end, and you have to figure out what the valid keyword is doing there. So it's harder to read and write, but it's a lot faster, and because you're able to vectorize and take advantage of the underlying capabilities of NumPy. So the goal of this project is to transform the standard Python code into NumPy code. And the main motivation here is for people with not much programming experience, or things like domain experts, scientists who don't necessarily want to learn all the intricacies of NumPy, get all the documentation, and figure out what all these different functions do. But it's a lot quicker and easier to just be able to write this top code and then translate it into that. So that's our goal. More specifically, our problem definition here is that given program P in S, which is our source language, we want to produce program P prime in T, our target language, such that they are semantically equivalent. Pretty standard synthesis problem. So our source language here is S, and this is it's a standard Python function. So again, it consists of fixed size loops, basic math operations, and conditional branches. So just very similar to the example we saw earlier. And our target language T that we're trying to translate into is our subset of vectorized NumPy array functions. So we've got our convolutions, sums, the where function, all sorts of things like that are what we want to be able to create programs in. So how do we do this? What's our approach? We want to apply program synthesis so that we can generate programs that we can then verify. And so the specific tool we're using in this case is called Metalift, which uses as a technique called verified lifting. It's called this because it takes the source program and then lifts it into a specification language. So then it can generate programs using the synthesis engine and verify, do bounded verification to check equivalence. So again, why verified lifting? We have a fixed set of combinators, our NumPy functions that we can combine and generate programs from. And then because we have those logical specifications, we can run bounded verification on them to verify our bounded equivalence. And then from there, we'll get our candidate programs that we can potentially run full verification on to ensure that it's equivalent to the original Python program that we have. So some components that we have here. So Metalift is not part of this project. We're treating it as a black box for the purposes of this. And so it takes in three different components. It takes in a source program, P, it takes in a set of specifications, and it takes in a grammar. And so the source language is where we get our source program from, and then the target language is what we write, is what we use for our specifications and our grammar. So these are things for the target language that Metalift then takes. Metalift will again lift it into a specification language, and then use the specifications and the grammar that you give it to generate programs according to that specification and grammar. And from there, it'll output the target program, P prime. So going a bit more in depth into these three components, first off, we have the source language fragments. So Metalift is specifically meant for compiling into a DSL. So the idea here is that you want to target specific fragments of your larger program that are computationally intense that you want to optimize for. And so in this instance, we want to have a single Python function. Again, for the ease of synthesis, we want to have it small, so that's why we have a fragment. And there's also some other restrictions due to the limitations of Metalift and synthesis in general. So the main one is that Metalift needs bounded loops. Metalift, and in general, theory of arrays is very hard. So the approach we went with here was to bound our loops with a fixed n. So for our arrays, we give them a fixed size, and then we can unroll those loops to have the computations just be straight line statements. So again, we bound the loops, we enroll them, and then we translate them from Python into C and C++. Because the final step there is to parse it into LLVM so that it can be represented as an AST, which can then be lifted. So we've got our source language fragments, and then next we need to have our specifications. So for each NumPy function that we have, we need to generate a specification for it. And this can be done by hand ahead of time so that users can just provide their source program and then get specifications and do the synthesis that way. So an example specification we have here is for the add function. For instance, it takes in two vectors, x and y. And you can see we've expanded this into a logical specification using first order logic. So we've got our x's, our y's, and our outputs. And again, we have to bound the size of the arrays. So we're bounding it at 4. And you can see we're expressing the logic based on what a correct output would look like. So this specification can then be run into something like an SMT solver to check equivalence, bounded equivalence. So next we have the grammar. So this is the search space of the target programs. This is what we're going to be generating programs according to. And here we just have a sample graphic of what such a search space would look like. This is obviously very simplified. The search space is very small, but it is a bounded depth tree that you construct based on what functions you have available. So in this example, we are simply supporting the addition and subtraction functions. And you can imagine that we're trying to synthesize here a function that takes in two parameters, x and y, and then computes some program over that. So with all that, we can look at what the implementation workflow looks like for this problem. So we start off with our standard Python code again. In this case, we're just adding together 3 arrays. And so our first step here is to bound it and unroll it, and then translate it into C++. So we've got some C++ code in the middle here. It's just been unrolled so that we have straight line statements all the way through that can then be lifted. And then on the bottom there, we have the actual lifting and synthesis that goes on, and outputs the program, which consists of 2 adds. And from here, we could then take that, and these are obviously bounded versions of the functions, but we could replace that with the unbounded versions of them, the regular NumPy adds, and then if we wanted to run full verification on that to ensure that it would work with the unbounded versions of the arrays. So how well does this work? So we've evaluated it on some different, evaluated the synthesis times, varying the depth and breadth of the search space. So this is sort of getting a sense for where we might be running into scalability issues. So you can see on the left here, this plot of synthesis time versus depth. You can see this curve is looking pretty exponential and is definitely indicative of some potential scalability issues. You can see once we get past 5, it's up to 13 minutes to synthesize. So that's definitely a direction for future work, is exploring more synthesis techniques and seeing how we can work with that. But on the right, a different plot is varying the breadth. So this is within the search tree, how many different NumPy functions do we support, and what range do we have there? And you can see that synthesis time doesn't really seem to be affected by the breadth. So this is an interesting result, and indicates that may not be a limiting factor in this synthesis in applying this. So with that, we do obviously have some directions for future work. The first is extending Metalift to support more language features. In particular, one direction is that supporting Metalift currently only supports one size of tuples. So when you're representing an array, if you want to specify, for example, the convolve function, you need to have multiple size tuples, so you can have a convolution that takes in two tuples and then outputs another one of different size. So we currently can't support that, but that's something that can definitely be implemented and support more functions. As well, we want to be able to compare the scalability with some other synthesis techniques, potentially eGraphs or Oracle-guided synthesis, to see how else we can approach this problem. So this has been an exploration of this particular technique and has delivered some pretty promising results. Are there any questions?
Hi, love the talk. Can people hear me? Can you hear me fine?
Yeah.
Great. One of the benefits that Metalift generally offers is this idea of verified lifting. That because there's an axiomatization of how LLVM works and how the target works, you can get this nice proof that these semantics are still equivalent. By translating initially from Python, you're missing one of the components of the certificate. Do you have an intention of sort of building up a formal translation to C++, or is the verification part not really part of the goal of this particular work?
Yeah, the goal would definitely be to have formal translation, because that definitely is a benefit of verified lifting, that you can get that verification that it's equivalent. So that's also, yeah, another direction of future work. Yeah, that's definitely an interesting direction, would be to sort of use, I mean, in sort of the exploration of other synthesis techniques, we could definitely explore other ways of searching instead of just using Metalift right out of the box. So, yeah.
Okay, thank you again to the speaker.